Hi, this is Matt Pelland here to talk about my compiler. I'm currently on task 80. So these are just my language objects, which are very simple. It's pretty straightforward. I didn't include anything in them that wasn't absolutely necessary, which is just their fields, something, a pretty printer, and a way to check if two expressions are equal to each other. So this is just the generic R language objects. C language, very similar. Same thing, nice and simple, only contains exactly what it needs. X language, again, just one object for every possible call that you can make. And then like an X program is a mapping of labels to blocks, which are a list of instructions. Very straightforward. So the first thing that we run is an optimizer. So I have this is simple, which really can be part of the optimizer. I just originally had it structured as a separate function because I didn't use it too much, and in the future I'm probably going to want to integrate it with the optimizer. I just haven't gotten to there yet. So as for the actual optimizer, is simple, just, returns true if there are no reads in it. Or in the future it will also check for set vectors. So in the optimizer you see this here, and that's going to be something you see very frequently in almost all of my compiler functions, where you can first pass it a program, and if you pass it a program, it'll just call itself on the program's expression and then return a program, because all of the work is done on the actual expression or the actual map of labels to blocks. And so this allows me to pass a program and get a program out even though all the work is in the expression. And then I have this environment object, which is something that I created here, which is really just a mapping of variables to values, except instead of being to a single value, it's to a stack, so that when I enter a new scope of a variable, or there's like two variables with the same name, I just push the new value onto the stack, and then whenever I reference that variable, I grab the top value of the stack, and whenever I leave that scope, I can then just pop the value off the stack and go back to whatever the old value for the variable was in that larger scope. And the other cool thing I have in here is just a genvar function, which will generate a unique variable for any given prefix. So that like my integers can be I and then a number, and then my booleans can be B and then a number, and it'll always generate them uniquely. So in the actual optimizer, it's pretty simple. So when I have like a negation, what I do is I first distribute the negation down into whatever its argument is, and then I just optimize that. So for example, like in special cases, or like if it's a number, I construct a number that is the negative of that number. If it's a negation, they cancel out, and I just pull out the child of the child. So if it's an add, I distribute it to each, etc. And so the optimization for add looks very long and complicated, but it's really all it's doing is it's saying, are there two numbers somewhere within me? If so, I can combine them and be done. And that, because that's one simplification. And then the other thing is, if there is a single number within me, then I make sure that it is always the sole argument in my left side, and then the right side contains everything else, because that makes it easier, so that if I have an add of two adds, I can just check their left arguments and see if they're two numbers, in which case I can pull them out, add them together, and be done. So that's really all that's going on here, even though it looks so complicated. And then if I come across a variable, if that variable is just a number or just a boolean, then I can get rid of the variable and replace it with the number or the boolean. Otherwise I return the variable. If it's a let, then we determine the value of the variable, which may be a number, maybe a boolean, it might be a more complicated expression containing reads. I push that into my environment object, and then with that in the environment, I optimize the expression of the let, and then once I'm done, I pop that variable off. And after that, if the let as a whole is simple, then that means that the variable is either a boolean or a num, so I don't need the variable at all. I can just use the optimization of the expression, which replaces all variables with their values, all simple variables. And then not very simple. If it's a bool, flip them. If it's a not, they cancel. If it's a comparison, then if it's a number or a boolean, check if they're actually equal in the case of an equivalence operation. If they're numbers, you can directly check if they're actually less than or greater than each other for this suitable operations. And then if it's an if, then if you're ifing on a not condition, then you swap the false and true. If it's a Boolean, you know which end you're going to evaluate, and you can ignore the other one. If it's a variable, then you can assume that it's true in the true side, and you can assume that it's false in the false side. So that's what's happening there, is we just pretend that the variable is in fact equal to true when we optimize the true side, and false when we optimize the false side. Otherwise, you just optimize the two sides as well as you can and call it a day, unless they're both equal to each other, in which case you construct a sequence. So as for the actual pass functions, the first one is just uniquify, and again, you see, similar to optimizer, we have the part where it can't take in a program, it initializes the environment, etc. And in this case, I'm using the environment to map old variable names to new variable names, which is why when I come across a variable, I replace it with the environment sub that variable. If it's a let, you construct a new variable, which is going to be unique, using the env genvar function that I made, and then you call uniquify on the value that you're setting the variable to, then push that into the environment, that the new var is equal to the old var. And you can't do that before here, because this might, if this contains any references to the same named variable, it's the more global one, not the new one, which is why this is after. And then you call uniquify, etc., and then you pop it off once you're done. So now Marble, you just exit, and then what this does is it looks into the object, finds all of its fields, and calls uniquify on them, because, like I said, all of its fields are just the children objects. So for example, if an if is passed, it'll automatically grab the cond argt and argf, call uniquify on them, and update the fields accordingly. So that just makes it very simple to write for all of the other things, because there's no real difference between like an if and an add in this case. It's just called uniquify on all of its elements. These are just some helper functions. And then resolve complex, I did pretty strangely. Again, you see, same thing here. Because the way that I structured it is like, here, we'll just jump in with add. So if I have an add, then what needs to happen is my left side needs to be a sequence of lets, which feeds into my right side being a sequence of lets, which then feeds into the actual addition of the two variables that are constructed, unless the left expression or the right expression are arguments already, in which case I don't need to convert them into variables. So how that works is my resolve complex takes var needed and tail, where var needed is the variable that I need to evaluate as, and the tail is what I'm feeding into. So that'll make more sense with an example, like for add. So first of all, if tail is none, that means that I am the first object in the expression. So like if the entire expression is an add, then evaluating that add, tail will be none, in which case I want to end evaluate as some new variable, which is going to be newly generated, which I'm going to set equal to this add, and then so it's going to be let new var equals add of whatever in new var. So what's happening is we first look if the right expression of the add is an arg, in which case you just use the argeval to right here, which will just map, again, I'm mapping of variables. If it's not a variable, you just return it as it is. And so that's in the case where it's an argument. If it's not an argument, then we need to construct a variable and set it equal to the output from a sequence of lets that generate that variable. So we generate a new variable to be the right child of the add, which is what happens down here. And then we set that equal to resolve complex, where we're resolving complex on the right portion of the add using the same environment. And we need it to evaluate or to create this variable rvar that we just generated. And it needs to feed into this child right here that I created, which is to let whatever that variable is be equal to this addition in whatever my addition needs to lead into. And then the left expression is similar. And the difference is, also up here, once I resolve complex on the right side, then whatever the new like child that the whole thing needs to evaluate as is whatever comes out of this, because this is feeding into that let. So whatever I do for my left side needs to feed into this. So that's why I set child equal to this resolve complex call. So then down here, I construct a new variable for the left side if needed. And then I once again update child to be the resolve complex of the left side feeding into child, which is the output of resolve complex on the right side. So then I have a bunch of lets that create a variable for my left side, which then feeds into a sequence of lets that generate the variable for my right side, which then lead into this let, to let whatever variable I need to be producing be equal to the add of those two variables in whatever I need to be feeding into. So it's kind of wonky, but it made more sense to me, and it does in fact work. And so it's similar things for negations and lets, using the similar kind of logic of determine what variable this needs to evaluate as to feed into me as an entity. So in the case of let, it's that you evaluate the value to feed into the variable that you're generating, which then feeds into your expression. So next is explicate control, which is very short, because that's really just converting to C-lang. This is still converting to C0. I haven't updated it yet. So So again, you see the program part where if it's a program, then we return a C program instead of an R program with the same info and a C label of body. It's just what I chose, calling explicate control on the actual expression. And so if it's an argument, then we just return econ of an argument, which just converts vars to C vars, nums to C nums. And then econ C will convert negations to C negations, adds to C adds, reads to C reads, etc. Very simple, and it just converts all of the lets into C sequences of sets. And so after that, we get to call uncover locals. Again, this is also very simple because this is still running on C0 when the only statements that existed are set, in which case we first check, are we a return, in which case we're done. Otherwise, we have constructed a info field locals, and then if we don't come across a ret, then we know that we have a sequence containing a set, in which case we just append that set's variable into the set of locals. This is going to need to be changed significantly with C1, because there are not only just sets and rets at this point, but for now, that's all it is. And then there's select instruction, which constructs the X code. Also pretty simple, because we just have two separate possibilities where we can select singular arguments, which convert nums to xconst, cvars to xvars, and then select statement will convert if it's an arg. So the other thing is the only statements that we have are sequences. So right now this is really not select statement, it's really select on a sequence of setting a variable equal to whatever this expression is. So if it's an arg, then you just move q the arg into the variable. If it's cread, you call read, move to rex. It's very simple things, just converting the c's into x calls to do the same thing. And then this section here is no longer used. That's assign homes. We aren't using that anymore. We are now, in fact, using assign registers, so I'm just going to jump to that. So first we have uncover live, which you can see here I have going through all of the labels in reverse and going through each instruction within that label in reverse because we're working from the bottom up. And I just have a new info field called live after, which is a list of one set per instruction in the program, where I just go through and I add whatever's live. So if you have an add queued, then both things need to be live before then. So you add both if they are a variable, but add if var isn't quite true because it actually also adds it if it's a register, because registers are also included in these live after sets. For example, if it's a move queue, then whatever you're moving, your source needs to be live beforehand, but what you're moving into your destination does not need to. Basic things, just constructs everything that's live at that given line and builds that. And then you build interferences, where you go through all of those lists that we generated there, and for every instruction you construct the interferences that all variables that are live at that time interfere with all other variables that are live at that time. which is what's happening here. But then what's down here is this bit, where we construct basically the move biasing part, where if we have a move queue where we are moving one variable into another and their live after sections exactly overlap at that move queue, so like if X is live up until that move queue and Y is live only after that move queue, and we're moving X into Y, then we add a move edge to our interference graph, which is just a different type of edge, which is then used in our coloring graph, which is down here. So what this does is, first of all, it goes through each of the registers, color the registers exactly what they are, because in my case, registers are just an enum of all of the different registers, so they have an associated value with them, so that's what I was using for the colors. And then you go through everything that it interferes with and add that restriction. So if it's a move edge, however, move edge means that those variables can be exactly the same variable. There's no need for them to be different. So if you have a move edge and you color something that has a move edge, then you automatically color all of its move edge neighbors to be the same color, so that they're just the same register. And you'll see that again down here, where down here is us going through all of the, so this restrictions array is the list of all variables that are uncolored and their restrictions. And so we go through, we find the most restricted one as the next one that we want to do, and then we call the assign color function, which just finds the lowest color that is not a restriction of that node. And then we go through all of its neighbors and add that restriction unless it is a move node. If it's a move node, we color it the same. Very basic. And then once we have the colors, we can call assign registers, which goes through each of the labels, each of the instructions, and it just calls assign reg on the instruction, which goes through. And so this is basically, if it has two arguments, then you call assign reg on a variable. So you first check if each argument is a variable. If it is a variable, then you replace that variable instance with its associated register. So when I was doing this previously, there were 13 available registers, and the first 3 are not available. So we just add 3 to its value to get to a valid register, if it's less than 13, in which case you just use that register. Otherwise, you need to use the stack, which is what this here does. Where, for example, if it is at 13, then 13 can't be used. You can only use 0 through 12, which correspond to 3 through 15. So in that case, you subtract 13 to get how far up the stack it is, multiply by 8 because each takes up 8 spaces, and put that into a deref instance. So very simple, just puts the variables into either a register if they can fit, or onto the stack. So after that you have main generation. Before that you have patch instructions, which pretty simple. It just checks if there are 2 memory references. If there are 2 memory references, you separate it out into 2 lines. Nice and simple. And then main generation figures out callee saved registers. It figures out how much space needs to go on the stack. For every register in callee saved, we determine if it actually needs to be saved, which is if we use it, which is this need to save. So that's if we use the register based on maxvar being the largest value register that we're using for variable allocation. So this tells us if that register is used by a variable in this function, then we add it to need to save. And then we go through everything that in need to save and we push it, and then we pop it at the end in end instructions. And then we construct our final program, which has begin instructions. It has the and then we move beginning to the beginning of the list of instructions, and then the end instructions. So you have begin, whatever you had before, and then end. So it's just wrap around everything. So as for actually running all this stuff, sorry, wrong thing. I have 2 different kinds of test cases setups, where one is just the test case and test suite, which will run test cases of the form input, function to run, expected output. So that's for testing individual passes. And then I have full pass tests, which are take in an original input what initial interpreter to run on it to determine what the value should be, and then it takes a list of all of the passes, which is what this is here. So for example, like it'll uniquify, and after you run uniquify, run interpreter R2. After you run main generation, run assembler X0, where those are just placed in my interpreter file, where I just have an R2 interpreter. I have my type checker interpreter for each of the other functions. And they're very basic, you know, like for an add, you interpret both of the children and add them together. This is all very straightforward, so I'm not going to particularly explain it. But then, so those are the two different types of tests that I have. And so if we want to actually look at it running, we can see, no. So this problem here is because I like to do all my assembly in Linux. So if I want to actually run the assembler, it needs to be run from WSL. So as you can see, when I'm running the test, it outputs what the test case is, and then for each pass, it'll say running the pass, what the result was. If the result was failure, it'll output what the pass produced and what the final answer of that pass was. And it passes all of the tests, runs every single stage with a compiler and correctly compiles. And you'll see that my optimizer isn't actually one of those passes that I use, because generally I like to run my tests without the optimizer, because I want to make sure that it'll work for any R program, not just an optimized one. So when I want to test the optimizer, what I do is I have my generate rand function actually takes a second argument, which is whether or not to allow reads. So if I don't allow reads, if I don't allow reads, then the function is fully optimizable and can be reduced down to a single number or boolean, in which case that's what this does here, is it checks if it does in fact optimize it down to a number or boolean, and it does in fact optimize perfectly any function without a read. And then I do also have individual test cases for reads to make sure that the optimizer works. So there you go, that's all of my pass functions for my compiler. They all work as of the checkpoint, and there we go. Thank you.